NASA's daily update on 3i Atlas just came out, and honestly, with the one line in secret everyone hoped to see still isn't there. There's no behavior stabilizing, no activity settling into a final pattern. Instead, buried in all that specialized language, is a pretty clear reality. 3i Atlas is not stabilized. If you've been following this object with me and you don't want to miss what happens if it keeps refusing to calm down, stay with me. Due to the current numbers, until the very end might be the clearest sign yet that this interstellar comet is still in the middle of its story, not the epilogue. Before we continue, if this has your attention, you can subscribe, turn on notifications, and hit like anytime. And for the best viewing, switch to full screen and enjoy what's coming next. The day began as any other check-in would. New images came in, fresh brightness measurements, position data from ground-based telescopes, and a couple of spacecraft cameras. Nothing concerning the plan implied that anything significant was coming. This was supposed to be just another point on a smooth curve view. No, an additional common data point that would confirm what we thought we already knew. On paper, that curve is simple enough. After perihelion, which is the closest point to the sun, activity should drop off. There will be less heat, less gas, less dust. The light curve slides down. The jets weaken. The comet's motion starts to look more and more like a still object that is simply coasting along its orbit, minding its own business. It's what happens to pretty much every comet we've ever watched. They flare up near the sun, then they calm down. Simple physics. When they laid today's brightness points onto that curve, it broke, and I mean really broke. Instead of following the predicted decline, the real data sits high. The comet is fainter than it was at peak. Sure, but it's still brighter than it should be at this distance, way brighter. The line that's supposed to bend downward just flattens out, like someone grabbed the curve and refused to let it fall. That's your initial indication that things aren't stabilizing the way they should. That's your first warning sign that something else is going on here. If this were just leftover dust hanging around from earlier activity, the inner coma would look soft and washed out, kind of blurry and indistinct, like fog slowly dispersing. But when they stacked today's deep exposures, that is not what appeared on the screen at all. The inner coma still has a sharp core with a fresh, faint arc wrapped around it, a new covering of material that wasn't in the stacks a few days ago. Think of it as a time stamp in dust. It's the edge of a recent pulse that's still close enough to the nucleus, in the form we can see before it fades into the background and gets lost in the noise. This is fresh activity, recent activity, not old material dissipating slowly. Farther out, the tail still has a defined spine. There's a bright, narrow lane running down its middle, supplied by a concentrated flow that's clearly still active. It's not diffuse. It's not spreading out the way you'd expect from dying jets. On one side, today's images show a slight thickening, like a side fan of material has strengthened. Again, like something turned back on. That's not the geometry of a system shutting down. That's a geometry that's being updated in real time. That is a comet that continues to do things. Then the rotation check comes in, and at this point, things really get interesting. To learn more about 3i Atlas spinning, NASA's teams watch how its brightness rises and falls over hours. Different regions of the comet's surface come into view. Some areas are more active than others. Some reflect more sunlight, so the brightness goes up and down in a pattern that repeats with each rotation. For a stabilized comet, the light curve repeats cleanly. Peaks arrive on schedule. The shape of the curve stays the same rotation after rotation. It's predictable, boring. Even, you can set your watch by it. Presently. When they folded the newest photometry over last week's best fit rotation period, the peaks drifted. They didn't line up the way they were supposed to. Something had changed. The main maximum shows up a little earlier than the previous cycles period forecasts. And there's a secondary bump that used to be small and fuzzy. It's grown sharper and more consistent every time it appears, at the same phase rotation right now, nearly as potent as the primary peak, like a second heartbeat that made the sudden decision to announce itself. Similar to a second active area that wasn't contributing much before, but now is a major player. That'll make everything line up once more. They had to cut the period slightly. That means the comet has spun up again, just a bit. The rotation is faster than it was last week. And that stronger second peak informs you of an important fact. A second active region has become a regular, reliable contributor to what we're seeing. It's not random anymore. It's not occasional. It's locked in. It's part of the pattern now. The spin isn't stabilizing either. It's still being nudged by forces we can measure but can't fully predict yet. Forces that are changing the fundamental dynamics of how this object moves through space. Now we get to the part that decides whether this is just interesting or genuinely unsettling. And that's the orbit solution. Every new batch of positions gets pushed through the orbit solver. It's a sophisticated piece of software that fits all the observations and figures out precisely where the comet is located and where it's going. Gravity does most of the work, right? The sun's pull, the planet's tiny tugs, all of that is straightforward. Physics. We've been doing this for centuries. We're really good at it. The difficulty is the non-gravitational force. The tiny rocket push from gas and dust jets blasting off the nucleus. When material vents from the surface, it doesn't just drift away. It pushes back on the comet itself. It's Newton's third law, action and reaction. It's small, but it's real. And it adds up over time, over weeks and months. It can shift the orbit in measurable ways. If 3I Atlas were stabilizing, those jets would be fading, and the extra acceleration term would slowly drop toward zero. The push would get weaker and weaker. In the ideal quiet case, where the comet has gone dormant and stopped venting, you wouldn't need it at all. The ellipse would be pure Newtonian mechanics, just gravity, which is simple and clean. Today's solution still needs it, and it needs it badly. Worse, it needs it in a slightly different direction than yesterday. That's the kicker. Using yesterday's non-gravitational parameters, the predicted positions and today's actual detections don't match. The residuals aren't random, scatter, as you might expect from measurement noise. They sway systematically to one side, which means the model is wrong in a specific, measurable way. The push has changed direction. To fix that, the fit has to tilt the thrust vector again and keep its magnitude at a level that simply doesn't match a coming object. The comet is still moving around in ways that keep changing day to day. The direction and strength of that push are evolving. So, you have three independent signals painting the same picture, three completely different types of measurements that all tell the same story. Brightness that refuses to follow the expected. Fade out. Inner structure that shows a new shell and a persistent tailspine. An orbit that still requires a changing self-push to explain where the comet actually is in space. And sitting over all of that is a rotation period that's still drifting, and a second active region that's become a permanent part of the heartbeat. That's what not stabilized looks like in real data. That's what the numbers are telling us right now. It's not one weird measurement. It's not one anomalous data point that might be an error. It's a consistent pattern across multiple independent lines of evidence inside the nucleus. In fact, it makes uncomfortable sense when you think about it. The pass near the sun didn't just scorch the surface and leave. It kicked off a slow, deep thermal process that's still working its way through the interior. Heat doesn't move instantly through ice and rock. It takes time, days, weeks, maybe months. The outermost material responded first. Obviously, soft ices, loose dust, shallow fractures. Those gave us the early wild jets and bizarre coma shapes that caught everyone's attention back when this comet was approaching perihelion, but 3I Atlas isn't a clean, uniform ball of ice. It's not a pristine snowball. It's a layered, cracked body that formed around another star, probably in conditions very different from our own solar system, and then spent billions of years in interstellar space, billions of years of cosmic ray bombardment, billions of years of micrometeorite impacts, billions of years of thermal cycling as it passed through different regions of space with different radiation environments. Inside there are buried pockets of volatile ice along ancient fracture planes, each at a different depth, each with its own threshold temperature, each one waiting as the heat wave continues to migrate inward, spreading through the interior like a slow wave. One pocket after another crosses its critical temperature. And when it does, chemistry takes over. Physics takes over. When that occurs, the region does not care that the comet is outbound and moving away from the sun. It doesn't matter that we're past perihelion. Temperature wins. Pressure builds. The ice sublimates. Gas expands. It vents. Every time one of those deeper pockets turns on, three things happen at once, and they all matter. They all contribute to what we're seeing. First, brand new gas and dust pour into the coma. They replenish what's already there. They keep the brightness exceeding what the models expect and carve new shells into the glow we can photograph. That's why the brightness is not decreasing, as it should. That's why we keep seeing fresh structure in the inner coma. Second, jets from new locations add torque to the nucleus. They're not coming from the same places the old jets were. They're coming from deeper layers, different parts of the surface, maybe regions that were dormant before. They twist the spin just enough that the rotation period and brightness pattern change again. So that's why the peaks in the light curve keep drifting. That's why we have to keep modifying the rotation period. Third, the direction and strength of the outgassing force shift. The total push on the comet changes, its magnitude changes, its direction changes, and that forces NASA to modify the non-gravitational term in the orbital solution to match the actual location of the comet against where pure gravity says it should be. From the outside, looking at our data, It looks like an object that refuses to flatten its light curve, refuses to lock in a spin, refuses to settle into a simple tail structure. It looks like an object that's fighting the models from the inside. If we could somehow see through all that ice and rock, if we could peel back the layers and look at what's really happening, it's a nucleus trying, and not quite succeeding, to reach a new balance under enormous stress. It's an object that got hit with more heat than it's experienced in billions of years. And it's still figuring out how to respond. Still adjusting, still venting, still changing. That's the real meaning of today's not stabilized update. That's what they're actually telling us. When you strip away the technical jargon and the careful language, it doesn't mean fragmentation has started. Let me be clear about that. There is no evidence of a second core splitting away. No clean row of debris trailing behind like breadcrumbs. No catastrophic brightening that screams breakup in progress. No obvious signs that the nucleus has cracked apart into major pieces. That's not what we're seeing, but it also doesn't mean we can treat this as a quiet, outbound comet anymore. We're past that point. We can't just assume it's going to follow the normal pattern and fade away peacefully. The data won't let us make that assumption anymore. A stabilized comet gives you predictable behavior, a rotation period that holds steady, cycle after cycle, activity that scales predictably with distance from the sun, following a simple mathematical relationship we've verified on dozens of other comets. A non-gravitational push that shrinks smoothly as the jets die down and eventually becomes small. You can ignore it when calculating the orbit. 3. Atlas is giving us something else entirely. A rotation period that keeps creeping, changing just enough each week that you have to keep updating your models. You can't use last week's value. Activity that stays high and pulses in waves that don't match the simple distance relationship. Brightness that refuses to follow the inverse square law the way it should. A self-push that is still required, still changing direction, and still linked to visible structures in the coma that we can photograph and measure. This isn't theoretical. This isn't just a rumor. This is what the measurements show. This is what multiple independent observatories are reporting. This is what the spacecraft data confirm. This is real. From here, there are really only two paths forward, and we don't know which one this comet is going to take. We're at a fork in the road, and the data hasn't told us which way we're turning yet. On one route, the deeper layers finish venting over the next few weeks or months. The heat wave works its way all the way through. The last pockets of volatile material exhaust themselves. The spin-up slows down and eventually stops. The rotation period locks in at some final value and stays there. The jets weaken as the last gas supplies run out. All of these curves finally start to slide in the way we expect, based on decades of watching other comets. Not stabilized becomes stabilizing and eventually just fading. The brightness drops, the tail fades, the structures blur out. The comet becomes a quiet chunk of ice and rock, drifting back out into interstellar space. Its story basically over. It had its time. It flared, it was interesting for a while, and now it's done. On the other path, the pattern continues. More late pulses of activity, more unexpected brightenings, more torque on the nucleus that keeps changing the spin, more stress on a body that's already been stretched, cracked, heated, and twisted within an inch of its structural life. More pressure building in pockets that might not be able to contain it anymore. At some point along that other direction, but we don't know exactly when or how the internal structure stops being able to absorb new changes. There's a limit to how much rock and ice can withstand stress. The fractures that have been opening and closing begin to remain open. The cracks propagate. The pockets of pressure can't be contained anymore. The structural integrity fails. The spin becomes unstable. The nucleus can't hold together anymore. So that's when not stabilized stops being just a line in a daily update and becomes the backstory for something more dramatic, something we'll be talking about for years. Something that might make this one of the most important interstellar objects we've ever observed. Right now. Today, we are unsure of the outcome, but today's daily check tells us very clearly, and without much room for interpretation, is that we are not at the quiet end of the story yet. We're still in the middle of whatever this is going to be. We haven't reached the resolution. We haven't seen the final act. The heat is still working its way through the interior. The pockets are still expressing themselves. The spin is still changing. The orbit solution still needs that changing push term. The brightness is still higher than it should be. The structures in the coma are still fresh and active. Every one of those facts points to an object that's still evolving, still responding, still under stress. This comet came from another star system. It was born somewhere else. It formed in a debris disk around a star whose name we don't even know. A star we probably can't even identify from Earth. It survived billions of years, drifting through the frigid interstellar void at incredible speed. It somehow ended up on a trajectory that brought it into our solar system. It dove closer to our sun than Venus orbits, experiencing temperatures and radiation it hadn't felt in billions of years. And now, moving back outward, it's refusing to go quiet as scheduled. It's refusing to behave. Every day that passes without stabilization is another day closer to finding out what happens when an ancient visitor from another star decides it's had enough. Another day closer to finding out what this object is truly made of, what it can actually endure, and what occurs when you push something from a different stellar system to its limits. The teams watching this comet are checking every day, now multiple times a day. Actually, new images, new measurements, new position data. They're watching the brightness. They're watching the rotation. They're watching the orbit. They're watching the structure and the coma in the tail. They're looking for any sign that tells them which path we're on. So, if you want to see whether tomorrow's update finally shows those curves bending toward stability, whether the brightness starts drop in the way it should, whether the rotation locks in and the jets eventually vanish, or if 3i Atlas decides to rewrite the script again and show us something we've never seen before from an interstellar object, make sure you're subscribed and stay tuned.